James, that was an awesome talk. I guess to kick off, we had one question from our very own Timothy Hume, which was, why do atoms jiggle in the first place, James?
Well, why do they jiggle in the first place? Oh, I mean, I don't know if I can answer that question. It depends what you mean by in the first place. So you could mean, why is there something called thermodynamics in the universe? And that is associated with kind of like the very initial conditions of the Big Bang.
Yeah, so James, I think some people just wanted to, and for people who also came in late and missed the introduction, just to review what if you've got an atom that's low temperature and not jiggling, what sort of causes it to start jiggling? You know, why do we go from having a kettle with all of this liquid water to suddenly having a cup of tea? Can you just sort of review that transfer of no jiggling to jiggling?
Yeah, so once again, there will never be no jiggling because we can't get to 0 Kelvin ever. Yeah. So there's always some amount of jiggling. And I've been calling it jiggling, but really it is energy. It's just that the average kinetic energy of a system can be associated with its temperature. And this average kinetic energy is kind of this random kind of thermal energy. So this random energy is always just going to be jiggling the particle, jiggling the atom in random directions. It'll never not be there because of quantum mechanics. It'll always be there. And we can turn the jiggling up by turning up the temperature, or we can turn the jiggling down by turning down the temperature, but it'll always be there. It's fundamental to the universe.
Yep. It's really fascinating how things seem to work similarly no matter what the scale is, isn't it, James? And touching on that, one of the questions we had from Campbell is, why don't all the atoms just pass through each other?
Well, I mean, they never really collide with each other, so to speak. Essentially, you have forces that act over distances. So if you have a charged particle, as it comes closer to another charged particle, this charged particle will feel the other one, and it'll start feeling the force before a collision ever really occurs. There's never really a situation, well, maybe in very exotic gases, where the particles will actually collide into each other. So I guess, is that an answer to the question? I think so.
Yeah, I think so as well. And touching on that, Brian had a question, which was, if atoms never touch each other, then how do we feel and touch each other when if I were to hold my hands?
Yes.
How do I feel it?
Yes. So atoms will definitely not touch each other. Under very extreme circumstances, you can have weird things happening, like an electron moving into the nucleus and things like this. But typically, I mean, even though I can feel my fingers touching each other, it's because this force, this attraction and repulsion force that I was talking about from electrodynamics, acts over distances. So it acts over a certain amount of distances. And we have kind of, our human experience says that, this kind of distance I'm showing you right now is my fingers touching each other, but at the atomic scale, these things are not touching. They're just repelling each other. And it's the same reason why my chair doesn't fall through the floor. It's being repelled by the floor in a certain kind of way. Yeah, so nothing is really touching each other on an atomic scale. Things that kind of bond to each other. And bonding is probably the more correct term. But yeah, things are not touching each other.
Yeah, and that makes me wonder, and Ariel's asked a great question just then, what would happen if there was no jiggling at all?
Yeah, so, I mean, thermodynamics, what would happen if there's no jiggling? So there's no temperature. So everything is very cold. Probably no Yeah, I'm not sure exactly what would happen. I mean, if ever in the universe, there would probably be no information transfer from anywhere else in the universe, so nothing would happen. But I'm not entirely sure. Yeah, we want to actually for a lot of engineering kind of techniques and stuff, we want to cool things down as much as possible. For example, in your computer, and it's because all this jiggling interrupts things. Of course, you want to send a message from one thing to another. If it has to go through a really jiggly kind of pathway the whole time, it's going to be interrupted and messed about. So in any kind of computer, we try to cool the system down, minimize the amount of jiggling, so things can transport information across paths really efficiently. And then you have things like superconductivity, where you try to reduce the jiggling so much that the transfer of electrons is really can just happen efficiently across the surface, for example. So if everything was zero, then I guess, I'm not too sure. I'm not too sure.
We'd be too cool for school.
We'd be very cool. Also, there's some ideas in cosmology about this vacuum energy that I talked about very briefly. So this vacuum is fluctuating everywhere. It's like this quantum vacuum, and it's to do with the uncertainty principle, as I talked about. If you take two rods and you put them really close together, I'm talking about, you can actually measure these fluctuations. You can measure these fluctuations, the force, because if you take two rods really close together, you can imagine there's fluctuations, really small energy fluctuations in between these rods, and it pushes them out slightly, very slightly pushes them out. So we can measure the fluctuations that way. And they would have to not be there in this universe, which has no jiggling. So perhaps people have talked about dark energy being associated with the energy of the vacuum. It's just one of the many theories. I'm sure Ryan will probably tell me that I'm wrong about this. But yeah, if we didn't have that, maybe we wouldn't have an expanding universe. But I'm not sure. I'm just hypothesizing at this point.
And it's so interesting how we've got all these different forces that are acting and creating things in different ways, isn't it? And Ravini is wondering, so if that's the case, that as stars are made of atoms as well, overall, why do they not show the same attraction or repulsion that we see at the small scale?
Yes, and that's because lots of forces act over a distance. And so we call them the inverse R squared forces, or inverse R forces. So essentially, depending upon how they act over those distances will kind of determine what is the most, I don't know what you'd say, dominant force at a particular scale. So for example, gravity is extremely weak on small scales. It's because electrons and protons and neutrons and things have very small masses. So gravity, the force is always going to be proportional to essentially the masses of the objects involved. But as soon as you make those masses really large, like you have an entire galaxy has a gigantic mass, it can really pull on another galaxy that has a gigantic mass. So the way that the masses scale up as you look at larger scales in the universe tells you that gravity is going to be a very important force at those large scales. Simply there are not, I mean, I was being a bit simplistic when I said there's no kind of, electromagnetic forces at large scales. There totally is. And I study those. It's just that they're probably not as important as gravity because we have such these really high mass systems. So I think that's the answer.
Yeah, and that's actually very interesting. And it makes me almost wonder about how things started in the beginning, which is a good segue into Yin Yang's question, which is, were there atoms during the Big Bang?
During the Big Bang, there were not atoms. So as someone brought up in the very start of the meeting, essentially atoms are made out of quarks, and you can get at these quarks, you can start looking at these quarks if you recreate the kind of environment that was around during the Big Bang. And we do these with particle accelerators around the world. We smash particles into each other. We create very localized, very very small kind of high energy systems. And these high energies are similar to the energies that we would have seen in the Big Bang. And you can split atoms apart. That's how high energy these are. And you can see the quarks flying out everywhere. Tim could tell you all about this. But very early on in the Big Bang, there would have been no atoms because it was too energetic. It was so energetic that everything couldn't even come together. Like it couldn't stick together with those kind of attractive forces that I was talking about. It was too high energy. There was too much jiggling, essentially. There was too much jiggling for even atoms to come together. And it really is actually associated with jiggling. It's associated with the huge amount of temperatures. The jiggling was so extreme that it pulled atoms apart. Atoms couldn't come together because the stuff that made the atoms was jiggling so much. So yeah.
Yeah, right. And it's that force is so violent, isn't it? And Sam and Jackson were wondering. They've got separate questions that are sort of related. So Jackson's asking, why do some things shrivel up when they jiggle? And Sam was wondering, do quarks jiggle too? And I was hoping we can give both Sam and Jackson an insight into how jiggliness is applicable when things are really, really small.
Yeah, I mean, quarks definitely jiggle about. Again, when I'm talking about jiggle, I'm essentially talking about energy, and they have some amount of energy. So they definitely jiggle about. That essentially inside an atom, it's like inside the nucleus of an atom, it's insane. Like everything is jiggling about. It's like a soup of jiggle, essentially. Like you have lots of things called gluons just kind of jiggling everywhere. And these gluons are kind of holding everything together. They actually contribute to the mass of the nucleus much larger than anything else in the atom, like the quarks actually. Yeah, so there's lots of jiggling going on. It's actually pretty funny. If you actually do the mathematics behind some of these things, you draw out some of these interactions and you draw them as kind of springs because they're so kind of jiggly. And what was the other question? There was the quarks question. There was something else.
Do quarks jiggle too?
Oh yeah, so I answered that one. That's yes, they do.
Yeah.
What was the other one?
When things become too small, why do they shrivel up? Is it because of jiggling?
So I'm not too sure exactly what the young star has in mind, but I mean, there's things like leaves outside that will dehydrate, and essentially all of the cells will become shriveled, and through this kind of like the cell is normally like nice and plump, but then as you take water out of it, it will shrivel down and crunch up kind of thing. Oops, my camera's over. It'll shrivel down and crunch up kind of thing. And the whole leaf, which is made out of the cells, will also shrivel and crunch up. So that's kind of a different phenomenon altogether. And I'm not too sure if that's exactly what the question meant, but yeah.
Yeah. We can always delve into one of our future talks. And because this is such a huge topic, as you already said, James. We've got time for 2 more questions. And I wanted to bring up a question from Wendy, which is it possible to crush atoms?
Crush atoms. Well, crushing, that's very interesting. So when I think of crushing atoms, I think of some very, very extreme environments like neutron stars. And essentially what happens in neutron stars is you fundamentally crush atoms. Yeah, so the pressure is so great. It's so great. The pressure from the gravity. So there's so much mass there. And we were talking about this before. The amount of mass in a system really determines what forces are the most important. And gravity is super important. It's just going to keep crushing until the electrons move in to the protons. So the electrons will come in and move into the proton, and you'll create like many, many neutrons. So an electron comes into a proton that creates a neutron. And this will be fundamentally, a neutron star is like a big big old neutron. It's just like a big neutron. It's so weird. So you have kind of crushed atoms in a kind of in a weird sense there. What makes it really hard is something called the nuclear strong force, and it is extremely, extremely strong, but it only acts on really small distances, extremely small distances. And it's the reason why it is so hard to push things into the nucleus. And yeah, it's much stronger than the attraction and the repulsion force that I was talking about, the Coulomb force. Much, much stronger. And that's why only in these really extreme environments that you get these weird things like crushing atoms. But yeah, I guess, I mean, that's kind of crushing atoms.
Yeah. And on topic of crushing atoms, young stars Sam, Lucas, and Wendy had similar questions, which is essentially, is there something that is smaller than quarks or atoms, and how did they jiggle?
Well, I mean, it depends what it depends what kind of theory you're interested in. If you're interested in string theory, then yes, there probably are smaller things. And are they jiggling? Yes, they are. So one of the kind of tenets of string theory is that you can describe particles as a set of strings in, for example, 12 dimensions, and the dynamics of this string, so the way that the string jiggles in 12 dimensions, will tell you information about the particles. And actually, this is quite a fundamental idea. So if you go to less abstract theories like quantum field theory, you'll work out that every particle is itself a jiggle of a field. So a field is something that is everywhere in space. So for example, we could talk about a temperature field, and that would just mean, like, you know, one part of the room, the temperature is like 32 degrees Celsius, and you move to the other part and it's 31 degrees Celsius. So if you just map out the temperature everywhere in your room, you'll create a kind of 3D field, the field of the temperature. So much later on in your physics career, if anyone wants to pursue physics, you'll work out that particles such as electrons, such as protons, such as neutrons, all come from jiggling fields of this kind of type. So the Higgs particle, the Higgs boson, is a jiggle from a Higgs field. So really, jiggling is very fundamental. I mean, I'm using it a bit wildly now, but it is very fundamental. Essentially, any jiggle in a field will result in a particle. And these are particles that we measure: electrons, protons, neutrons. Yeah. But yeah, maybe this is a bit off topic now. I don't know. I like this kind of stuff.
Yeah, we've got so many more questions from Ronan, Iram, Jackson, Michelle, Campbell, Declan, Lucas, Rubini, but we've run out of time, guys. And what we'll do is we'll go through these questions, and we'll try and get to them through email or one of our future videos or in one of our future talks. But please join me in thanking James for making me feel very jiggly about how stars are formed and how cooking works in our kitchens.